Hi everyone, Mr. Barden here. Today I'm going to be talking a little bit about the basics of electricity and how we can use that in order to build circuits that we will later be getting into with some Arduino code. This video is kind of setting up the final unit of the Programming Digital Media course. Normally I try to get several videos out at once, just so you can have a few things to look at and go through at your own pace. However, for this section, what I'm going to do, because this will involve some fairly complicated video setup with multiple cameras, because you need to see my hands and the circuits I'm building. I'm going to be essentially recording my class sessions and the demos I'm giving there, and you'll be able to see the circuits I'm building in real time as we go along. So there are more videos coming. I just won't be posting them all at once like I normally do. You'll kind of see them throughout the week for about 2 weeks or so. With that being said, let's just dive right into it. Let's get started. So I have these slides here. You can find a link to them in the description if you want to kind of look at them on your own. But basically, we're going to talk about the idea of physical computing. So far in the PDM course, all we've done is the virtual computing. Things like that. We've been typing the code and running it on the computer. What we're going to be focusing on now is, again, kind of pathing out all of the electricity, setting it up to run physical items in the real world. And that will involve, again, the idea of electricity, and it will still involve some code, but we'll kind of get to that as we start building this. So again, some of the things that we need to use for this course, we have electronics right here, and that's what I'm going to start off with. Is just, how does this work? How can we hook a lamp up to a battery and get light out of it? We have things that do stuff, the various components, power sources. Those are kind of the main things. We have microcontrollers. Again, we'll be using Arduino. If you're doing this on your own, or you're finding this video for another class and you don't have a specifically Arduino board, that's okay. There's a lot of comparable ones. I technically don't even own an Arduino brand board, but it's Arduino compatible. So we'll be talking a bit about that and a bit about writing the code that goes along with that. So again, we can program these controllers to send out electricity and respond to changes in electricity in specific ways. And that's going to be the goal of this unit, is to get our boards to, send out the electricity for the things to do things in the real world, have the circuits change the amount of electricity going into the board, and have the boards react, and then have our board communicate with our JavaScript code in P5. That's going to be kind of the final section of this course. So I'm going to be talking a little bit about how the code is a little different in a later video, so you can check that out. If you go to a link in the description, the textbook for this course, you can kind of see some of the specific differences between the Arduino code and the JavaScript code. They aren't that different in terms of structure and concepts. However, some of the things you have to type do vary, just because the Arduino code is built out of C, whereas we're focusing on JavaScript in P5. All right, let's move on. All right, so what is electricity? We've been using it, throughout this whole course. Your computers need electricity to run, and the internet needs the electricity to serve all the things and whatnot. And I'm sure you have it, all throughout your life. But have you ever thought to think about what it actually is? So on the atomic scale, so everything is made up of atoms. They're very tiny. There's kind of three main components that make up the atoms. The protons, these are components that have a positive electrical charge. The neutrons have no electrical charge. And then the electrons, these have a negative charge. And these electrons, I should have a diagram on this slide now that I'm thinking about it, but they circle the clump of protons and neutrons in the middle of the atom, and they circle around it. And because of that, they can fly off and jump around and move from place to place. I'm simplifying this a lot. But this flow of electrons is electricity. Again, if you take a bunch of electrons and move them from one place to another, you've then got a large change in electrical differences between these areas. It's a flow of electricity. So again, we have these electrons, and they don't always move. There's kind of two main, again, broadly speaking, kinds of materials. We have insulators and conductors. So an insulator is an object where those electrons cannot freely move very well. So again, air is a fairly good insulator. So again, if you unplug something from the wall, the electricity doesn't, jump across the room and connect back to the plug. It shouldn't, at least. And that's the air is insulating those electrons from moving around. Wood, things of that nature. That's just electricity does not travel well through. Other things that electricity flows very well through. This could be water, a lot of metals, things like that. Those are called conductors. So again, you could send electrical current, this flow of electrons, through these conductor items very easily. It should be known that if you try hard enough, you can get electricity to flow through anything, even if it's an insulator. You see, lightning will travel through the air. We won't be doing anything near that powerful or dangerous in this course, but if you don't go around like poking into electricity in the wall and things like that, just knowing, just because it is dangerous, and again those voltages are a lot higher than the ones we'll be working with. So these are all very low level things that, as long as you're not just trying real hard, you won't get hurt. So I just wanted to say that before we move on. So there's three parts of electricity that are going to come into play for every circuit we make, and that's the voltage, the current, and the resistance. You've probably heard some of these words before if you're ever mildly interested in just electricity, and just hearing it used. So again, voltage, current, and resistance. These are kind of the three basic elements of electricity, and they're going to come into play in all the things that we're building. So let's take a look at how they work. These items are all related. So I like to start off with kind of this diagram of a water pump or water tank. Or we have this kind of law of physics breaking diagram right here, where it the water flows down, goes through everything here, and it goes to blah blah blah. But basically, we have the amount of electricity that's flowing through this circuit. That is the current of the electricity. Okay. The difference of it, the voltage, what's kind of pushing it through, that is the voltage. And then anything that kind of blocks or slows down the flow, that's the resistance. We're going to get a little more into detail with each of these as we go, but just think of it this way. You have the water tank up here. It's flowing down through the pipes, and then you have a water pump that's pushing the water back up to the water tank, where then it flows back down. Again, this is a cyclical thing that goes back and forth. It's working through here. So again, the water flows down, it's going through here, and then it's resisted by these changes. Well, again, we're about to go through all of them in a lot more detail, but these are the three main things and kind of how they're related. All right, voltage. This picture is going to come back for a few slides. So again, this is the force that pushes the electricity through the circuit. Okay, so the more volts, the more the electrons are flowing through the circuit. Potentially, the more dangerous things can be. But again, it's the relative energy between any 2 points. All right, you can think of it as again, if in that water example circuit here, the voltage, that's kind of that gravity that's pulling the water down through the circuit. In this diagram here, the voltage is pushing the current through the circuit. So, all right, and again, we measure this in volts, a lot of times just represented as a V in the math. All right, the current. The current, measured in amps, that is the flow. That is the electrons themselves that are flowing through the circuit. So the voltage is what's propelling the electrons. The current measured in amps, or technically amperes, shortened to amps. That's how I'm going to refer to it. That's again the flow of it. So again, think of it. You got a big roaring river right here compared to just a little trickle to keep that water theme going on. So again, at any point in your circuit, you can measure how much of the electricity is flowing through, and then that's the current or the amps of the circuit. So again, you've got in the diagram the voltage is pushing the current through where it's getting resisted, and we're going to talk about resistance next. All right. So resistance. Everything that we make these circuits out of has some kind of resistance. Again, the conductors have very low resistance, and the insulators have very high resistance. The current, the amps, always travels through the path of least resistance. That's why you may notice a lot of times lightning hits very tall objects, because it's traveling to that closer point. There's less resistance than if it would have traveled all the way to something farther away or a lot lower. To use the river and the water diagram, if you have a bunch of rocks in the water as it's flowing through, that's going to cause more resistance. It's going to take more work to push the same electrons or the same amount of water through the river. All right, and you always measure it between 2 points. It can be referred to as a load. Right there, we measure it in ohms. So again, using this diagram here, we've got the voltage pushing the currents through the circuit, but the resistance, the ohms, is squeezing it down, making it harder to get everything through the diagram, through the circuit. So again, the more resistance, the harder it is to push the electricity, and eventually, if you have too much resistance, the electricity just won't flow. All right, so notice the wires that we'll be using for all this, they have a resistance, but it's much less than the insulators on the wire and the air. So again, the electricity will flow through the wires, but it won't travel out through the air and shock you. So long as you aren't doing something stupid. I don't want to talk in absolutes, but generally speaking, that's what's going to happen. All right, power sources. So power sources, things coming, basically when we plug in all of this, whether it be to a battery or to the computer or something like that, or just the wall, the power is coming in. And these, again, are like the pump in that example a few slides back that was pumping the water back up into the tank so it would flow back down, and it formed this loop. And basically, it serves to energize the electrons. It takes the ones from a low energy at the ground part of the circuit and gives them a higher amount of energy. So again, it's like moving water up a hill or to the top of a water tower, and it flows down from there. That's what creates that pressure, that voltage. And then just like water, electricity goes from that high to low energy, unless it's blocked by the resistance or insulators. Again, the low energy side is called the negative or the ground energy, and the higher energy side of a battery is called the positive. We'll see this a lot in making the circuits. We have the positive side and the ground. Okay. All right, and then the voltage of a battery is the difference between those things. So a 9-volt battery puts in 9 volts of voltage between the positive and negative ends of the battery. Just a quick example. All right, so how are these things all related? As you've seen through all the various diagrams, these things are related. As you increase the voltage, it would affect the amps and the resistance and things like that. There's a formula that kind of goes through all of this, and this is called Ohm's law. Ohm, the same guy, resistance, we measure it in ohms. That's the scientist that worked all of this out. So voltage, current, and resistance in a circuit or just a part of a circuit they're all related. You have the voltage, the current, and the resistance. V, I, and R is how we do it in this particular diagram. So the current is equal to the voltage divided by the resistance. And you can very easily figure out any of these three elements just by rearranging this equation. You can get the voltage is equal to the current times the resistance, and the resistance is equal to the voltage divided by the current. These will all come in handy because, as we'll find out, we need to have very specific amounts of resistance in order for our circuits to work properly. All right. We can also kind of work out things to get the watts, the power of some of these elements. And again, the watts is equal to the volts times the amps. So to get the watts, we don't have any I times V here, but if you again, power equals volts times amps. So if you ever need to figure out the watts of the circuit and you know these things, you can figure that out. All right, let's make a circuit though. Let's move on to some of the more exciting things. So a circuit, this is a key thing. It's a closed loop. All right, it's always connected. My picture's kind of hiding the thing. Let me move that. USB camera. There we are. So it's a closed loop. So it's always connected from the positive end to the ground end. And then we have the power source, that battery in the middle that then serves to re-energize things, moves from the negative back to the positive, and we get this cyclical loop, this current of electrons flowing back and forth and around and around and around, and that's what generates this electricity. Generally, we get the flow from that high energy side down to that low energy side. So the resistive components usually do some kind of thing. The lamp, in that case, sometimes they'll have motors and stuff like that. Do want to think about something real quick, and that is if you had no resistance at all, what would happen? If I go back to, we're going to see Ohm's law again. If I go back here, so if we had no resistance, we're going to get this case of the current is equal to the voltage divided by 0. You think for a second, try to divide something by 0. That's a problem. And basically that's what's called a short circuit. The electricity is too much flowing through, too much everything, it overloads. The electricity ends up basically blowing up. It can't circuit anymore. That's a problem. And that's why we use some of the wires, and we'll have specific resistor components that help to avoid that. A lot of modern things have ways to help prevent this built into them, but we still want to be careful and be sure to include the right amount of resistors in our circuits. And then the conductors, again, the wires essentially are used to specifically route the electrons from the power source to the components they want to power and then back down to ground, so that way we can form this loop. As we can see kind of here in this diagram, here's the wire. With the arrow, we can see the electricity flowing to the lamp and back to the battery. All right, I'm going to bring my camera back. There we go. All right. So again, thinking about what I've just said, would this work? Would this be a circuit that would power a battery? Power a light. This is a video. I'm not going to wait that long. The answer to this one is no. How about this? You might think it looks a little more better than the last one, but not quite. Last we have this one here. I'm going to talk about each of these for just a second, but this is the one that would work. The reasons the other ones wouldn't work is that this is not a cyclical setup. We just have the wire connecting from positive on the battery to the lamp. There's nothing connecting to the ground. Okay, so again, the electrons cannot flow in a cyclical pattern to produce the electricity that we need. This one, we've got a little bit more of a setup here. It also would not work because even though we can kind of get this set up here, we have the lamp connected to the positive end of the battery. We have the wire also connected to the positive end. It's not moving from the positive to ground. All right, again, nothing's moving to the ground. It's still not going to flow how we want. The electricity only flows in one direction. This one here would work. So we get the lamp connected to the positive end of the battery, and then we're going from the wire to the negative end, so the electricity, following my mouse here, can flow in this circular direction, and it could power it up, assuming that all the resistance is correct, as I mentioned before. All right, again, here's a diagram with a better little arrow here. It's this closed circuit. It's the cycle is repeating. We're going negative to positive through the components back to negative, or positive through the components to negative back to, but wherever you start, it loops back on itself. So the circuits, the electrons in the circuit can move in this pattern. All right. So again, we've got kind of a basic understanding of what electricity is, what goes into it, things of that nature. Let's start talking about some of the components that we'll be using in this unit. Specifically, some of the ones that we'll be doing, resistors are going to be very important, some switches, LEDs we're going to be using a lot of, and a few other things. All right, so a resistor. Again, these resistors, as I mentioned before, resistance is measured in ohms, and we generally have to add that to our circuit in order to work. They generally work by converting the electrical energy into heat. So if you have very big resistors and a lot of electricity running through it, they can get hot. If you have a very small resistor on a very powerful circuit, they could overheat and essentially blow up. You don't want that. We will mostly in this course be using what's called fixed resistors. So again, you connect one end here to the circuit, you connect the other end to the circuit, and the electricity is going to flow through the wires. And you can see as these keep getting bigger and bigger, they have more resistance. Another thing we'll be using is called variable resistors, or potentiometers is how I'll generally be referring to them. And these can change the amount of resistance. So in this case, you can see this one's like a sliding switch. This one's a dial that you turn. But as you move that back and forth, the amount of resistance increases or decreases, contrasting these ones here where it's always the same thing when you plug it in. These have some specific symbols that you'll notice. Again, we'll get into diagrams as we go along, but if you ever see this symbol right here, that means that it's a resistor. In my experience, I mostly see the squiggly line ones for a resistor and the squiggly line with the arrow here in the middle for the variable ones. That's just in my experience. You could see a few different options. Okay, so I mentioned the fixed resistors have a specific amount of resistance for them, and that doesn't change. The way that you can notice, though, in most cases, it doesn't tell you what it is. It has just a series of bands on them. That band serves to tell you how much resistance is here. So basically the way that we go about is I think most of the time we'll have 4 or 5 band resistors. Sometimes you could even have up to 6, but I think all the ones from my students at least are 4, but you can also very commonly see 5. And these color codes mean a specific thing. So basically the gold and silver I use these to help align my resistors and look at them from the right direction. And this is the tolerance within it. So again, all the each individual resistor might vary. So again, within 5 or 10% of some of this stuff right here. That's again where that tolerance could be. Most of the ones that are used for this class will be the gold right there. So I do that, and you'll notice you'll want to line this up on that right side. So that way you know you're looking at it from the right angle. All right, and again, notice gold and silver are the ones are only used for the tolerance, and most of them tend to be that. You can run into brown and reds, but most commonly you'll have the gold one. That's kind of that sweet spot of easy to produce and still high enough quality to do most things for the Arduino. So if you line that up on the side here, we'll be able to then read these other bands in order. So you have the first one right here, and that's just lined up, corresponding to a number 0 through 9. The second one is also the same. The third one serves as a multiplier of the first two. So again, this one's a 27,000 ohm resistor, and as an example, so we get, as it's red, 2. Then it's pink or purple, that's 7. So 27. And then the last one here is this orange right here. So that's times 1,000. And again, it's just the number of zeros. So times 1, times 1, so that's 0 zeros. Times 10, so that's 1 0. Times 100, 2 zeros, and so on. So that's 27,000 ohms. I think most commonly in my course we'll be using the 220 ohm for the LEDs, but this could vary. And this is how you read that. I generally put up a diagram of this for all my students, but just know that this is a color coding system, and this moves kind of in the order of the rainbow, Roy Jibiv, and then the other stuff. So again, you can read that through right there. They have a maximum wattage. The ones with the Arduino kits, they're all rated for a 1/4 watt. We don't normally have to worry about that because we're only going to be hooking it up to the power that it's designed to hook up to. But again, you can kind of look through all of these. So again, here we have 15K on the 5 band. So 1, 5, 0 times 100. So 150 and 2 more zeros, that's 15,000. And we have 620,000. So again, we have the blue, that's 6. We have the red, that's 2. We have the 620 times 1,000, 620,000. And then stuff for the right here with the resistance and the things of that nature. We don't normally have to worry about these as much. So again, that's how those are all set up. Here's an example of a resistor again. Here's that 220 ohms. You get the red, brown, and then it's really hard to see, but then there's the gold band right there. These are all fairly small, and you'll just have to get used to it. And I say red, it's approximate, but you'll be able to tell the difference from each other, and you'll get used to that as you go. So I kind of gave away the answer, but we have that one right there. Okay, switches. Switches are important. These are designed to interrupt that flow of electricity. So again, I've got this diagram right here above my camera. So again, this line represents the wires that the electricity would flow to, and we have the switch here. So it's either not connected or you connect it. There's a few different kinds of switches, but essentially you're able to either connect or disconnect the lead, which allows the electricity to flow or stops it from flowing. We have this one right here, this kind of toggle switch, and these work basically the same way. The toggle switches, and again, basically the electricity will flow in through one pin, one lead, and then based on the state of the toggle, it will flow out through either the middle one, or the third one. And it works the same way right here. This is, so again, and these switches keep their state until you change it. It's like a light switch. Okay, so you flip it on and it stays on until you flip it off. A momentary switch, like a push button, is you press it, and when you let go, it goes back to that off state. So I'll be using, mostly the momentary switches, but again, current's going to flow through on one side of the switch, and then when you press it, it's going to come out of the other. But then when you let go, it stops by default. It doesn't keep the current going until you tell it to stop. It automatically stops. So you would have to hold the button down for as long as you wanted everything to be on. There's pros and cons to each of them. It just kind of depends on what you're wanting to make for which one you'd want to use. There's also a tilt switch. We won't really be getting into this that much, but basically it's a little oval kind of cylinder shape with two pins, one where the electricity goes in, one where it comes out. And when it tilts, the metal ball rolls over and touches it, so the current would come in, go through the metal ball, and then out the back one, because the metal ball would be a conductor, and that's just how a tilt switch works. I don't plan us, my students using this a lot, but if you need to, this is how it works. What we will be using a lot is a type of diode. And a diode only allows electricity to flow in one direction. A lot of the things we've seen so far, if you could take it, turn it around, and put it back in the circuit, and it would work just fine. It would probably be the opposite, but it would still work. They were bidirectional. And a diode is not. It has a specific positive and negative in. The anode and the cathode is what they're called. Again, the positive and negative in. These components will only work when plugged in one way. The ones that we use are the light-emitting diodes, or LEDs. I'm sure you've heard of an LED light before. But this is what we'll be using a lot in this class. They come in a variety of sizes and colors, and things of that nature. But basically, as the electricity comes in and jumps across to go out, it produces light. And then the things around it can help filter that light to look how you want. As we work with LEDs, you'll notice that one lead is longer than the other. This longer one is the anode, the positive end, whereas the negative one is the shorter lead. So as you'll see, as we start putting these into the breadboards and making the circuits, and in those videos that I haven't made yet, you plug it in, say you have it from the battery to the LED, you would plug the positive end into that side, and then from the negative end, that would go to the resistor and to ground. So again, that's how we set that up. These use very little current, usually run off of 3 to 5 volts. So these are not very hard to use, and we'll again get into this very quickly. If you do have these in backwards, best case scenario, it just doesn't turn on. Worst case, you can actually blow out the light and it breaks and never works again. So again, just always double check which way it's facing into the circuit. Other components, some things we may need depending on what we make. A capacitor stores water to be in it, or stores electricity to be released at a later point. So it's almost like a tiny little battery. Again, it holds electricity and then boom, pops it out. So you can use it to help power motors and things like that. We don't. Those are measured in farads. We don't need to go too much into that right now. A transistor or a relay are like switches, but these are controlled by an electronic signal from the Arduino. So if you wanted to use a transistor, you could send the signal, and it will automatically do all of the turning and things like a manual switch. There's many other things. This is only scratching the surface, but I wanted to kind of touch on just some of the more common ones that you may run into. All right, so you may have noticed these symbols here. Again, as we make these circuit diagrams, there are certain symbols that represent things. So again, the straight lines, those are essentially the wires, mapping out the current going from one spot to another. And each component has a different symbol. So again, we see the resistors, the switches, the LEDs, batteries, things like that. So we can see that in the diagrams. So these also have some names here. So again, you can see abbreviations: resistor, capacitors, inductors, switches, LEDs, things like that. They have a letter abbreviation. So here's a real basic example one here. So again, we've got a battery of 3 volts. The positive end is going to a resistor of 220 ohms, to an LED. It's a red one here. And again, we can see the positive and negative end is that straight line, which then goes back to the negative end of the battery, this short end. So again, this would be the circuit. This will actually be the first circuit that we make in this course. So stay tuned for that video. That'll be the first thing that my students are going to be doing. All right. Simple circuits. So as we make these, there are 2 main kinds of circuits that you may run into: a circuit in a series or parallel circuits. So in a series circuit, all of the components are in a row. In this case, with light bulbs, if anything here breaks that thing, so say one light bulb goes out, it's going to stop the flow of electricity for everything. So again, we've got this looks like the positive end of the battery going through here to the next one, back to negative. So as soon as one of these breaks that signal, it's going to stop all of the electricity for everything. This is different for a parallel circuit. A parallel circuit has many different routes for the electricity. So again, the positive here goes out, and then on here it branches off and can come back to the negative. It also keeps going and branches off and goes back down to the ground, and so on and so forth. So if one light, in this case, goes out, the others would stay on, because instead of forming one loop with 3 things, you're forming 3 loops, each with one thing. So that's kind of the main idea between parallel and series. And you may run into an issue with your circuits, depending on how you build them, where again, if you take one thing out and all of a sudden the other stuff stops working, you may have then built a series circuit instead of a parallel one. So depending on what you need, they have different contexts and pros and cons. Generally speaking, we're going to be doing a little bit of both. So like if I make a switch to turn an LED on and off, that'll probably be a series circuit. But if I have a bunch of stuff all happening at once, that'll all be in parallel, so I can focus on one thing as opposed to, stopping one thing and it breaks everything else. So again, we'll be doing a mix of all of that. All right. So again, this is just kind of showing that series circuit. So again, we got some things right there. There's only one way through it. So again, the current would have to go through both of these resistors. As it goes through, the current's the same. The more resistors you add, the more resistance there is to the circuit, the less current can go through everything, because again, the current has to go through everything in the series before it gets back to ground. Parallel. So again, there's 2 paths from positive to ground. We can go through the first resistor here, or the second one. And the amount of current through each branch depends on the resistance right here. So again, higher resistance, less current; lower resistance, more current. And again, that kind of branches off. The way that we'll be building these circuits, as we're approaching the end of the slides here, is with a breadboard. This is a great tool for helping to prototype your circuits and connecting everything together. The holes in it are kind of designed to match up a lot of the components that you may run into, so you're able to kind of push the wires just right into the holes. These are set up in a very specific way for routing electricity. We can see that the top of one here is kind of like a grid. On the back, you'll notice these kind of metal bars. So they have two on each side that run down the length of the breadboard, and you can see that's positive and negative. So that's where you would connect the power and ground portions here. And then there's a bunch of horizontal lines. So let's say I connected my power and ground, and then I used a wire to jump over to here. Everything in this row would then be getting that power. So I could then connect things to that row and have it branch off into series, things like that. So again, everything connected to this row right here is all getting power. Everything connected up here is all getting the same power and ground. And it makes it very useful for routing that electricity. Again, as you do more and more of this, this will become a lot easier to understand. So if the diagram's a little weird, don't worry. As you start getting your breadboard out and plugging things in, you'll kind of understand it as we go. All right, wires. Again, connectors. You'll sometimes hear these called as jumper cables, like to your car, but much smaller. But just the wires in general. The metal component inside. These have. These are good conductors with an insulative, sometimes rubber coating around it, so that way you can touch it and they can touch each other and it won't short out the circuit. Basically, you're going to want to exclusively use red for connecting to the positive end of your battery. That's basically what that's for, like almost exclusively. That being said, if that's all you have, you can definitely use it for other things. The wires are basically identical on the inside, especially for these kits. They're identical. It's just different colors, so you can tell what's going on. But generally, the red wires are in practical applications are always used to connect to the positive end of the battery. So again, anything that's getting electricity from the positive end gets the red wire. Black, sometimes green, but usually black. Goes to ground. And again, use those like that first, and then if you need to use a red wire or a black wire for something else, you can. It's not going to break your circuit. It can just get a little confusing for people looking at it. The other colors are just used for wiring up your various circuits. So again, you'll have a variety of colors in your kits. You may notice two different styles. I think most of the kits come with these here, and these have a more flexible core to the wire. So the wires bend and then they go back to their initial shape, whereas these ones right here have a thicker core, so you can bend them and they keep their shape. They're used for slightly different applications. So most Arduino kits come with the bendy wires, but you may see some of these ones that bend and retain their shape. They work the same way. All right, this is an important thing here, and that is that the right and left sides of your breadboard are not connected. You're going to notice this groove going down the middle. And then, so again, all the things on this side, you have this positive row, this negative row, and then these horizontal rows that are all connected. So again, the 5 row is connected, the 6 row is connected, and so on and so forth, and all that. So you could either connect both sides to your power source, or to save power sources and batteries and cables, you can just jump from one side to the other, so that way the power all connects and flows properly. So this is basically how I always set mine up, so that way both of my sides can connect to the power. So again, I just get positive going to positive, negative to negative with those jumper cables. Again, red being positive, negative being black. So again, if for some reason it's not all working and you're going between both sides of your breadboard, make sure that you've connected both sides to power and ground. All right, wiring from a circuit diagram. So what I have here, this diagram and this diagram are the same thing. This is made in the program Fritzing. It's a paid app, but it's really good for making a lot of these diagrams. I have a whole little video going through the online platform Tinkercad, which does a lot of the same thing. I don't think it does these diagrams, however. But anyways, let's look at everything going on here. So we have a battery with the positive going through a resistor, and then from that resistor to a switch, from the switch to an LED back to ground. Let's see if I can zoom in. No, I can't zoom in. All right, so it's a little small to see, but again, we have the positive into the battery, into the breadboard. We're then connecting from that positive end to the resistor, through the resistor to the switch. And then again, we see that the middle pin, that's connected to the LED. The third pin is not connected to anything. So again, that third pin's not connected. That middle pin is connected here. We see it's to the wire, to the LED. There's the positive end, the longer wire, to the negative one out there. And then black wire takes it back to ground, which then takes it to the ground end of the battery. So again, it works the same way. And then this switch will be able to just toggle on and off the LED right there, by either connecting or disconnecting the flow of electricity. All right. So again, this will be an activity where you'd want to draw what's going on here. But basically, again, you've got the 5 volts coming in to an LED. Again, that longer wire being the positive one, through the LED, through a resistor, which then this one's a diagonal switch. So diagonal, so when you press the button, it completes the circuit and runs to ground. This is the same one, and it's in parallel here. So again, this is its own 5 volt to ground, and this is separate from this one that goes 5 volt to ground the same way. If this was to change, that would go from the LED, from the resistor to the other one, you'd have to hit both buttons and both would turn on at the same time. But because these are parallel, they work independently of each other. And that is the end of my slides. I kind of took out a lot of stuff that's kind of a reduced version of the college version of this course. And again, that's going to kind of go through a lot of the information you might need to know. Again, over the next few days, I'm going to be essentially recording my presentations on the various topics and various bits of circuit building and posting these online, both for my students to look at after the fact and anyone else who's just wanting to learn more about the course. So again, this has kind of been the basics of how electricity works and wiring up circuits so that we can use them with our code. All right, and that's going to be it for me today, so I think I will see you all the next time that I see you.